Hello, this short little video is about the celestial sphere. The celestial sphere is an imaginary sky. It looks like a big clear ball. This is a representation, a picture that you may have seen a celestial sphere as decorations in a home or business, or perhaps even have seen one in a museum. Celestial sphere is not real, but it's a useful way of talking about the sky. Celestial sphere typically is shown as a clear globe, plastic or glass, and the Earth is at the center, and the stars, sun, moon are all about the sphere as we see them in their constellations. Of course, this is not real. It's only convenient. It's a convenient way to talk about the sky. Here's a simple celestial sphere, a very big globe, very, very big. It's round, it's a sphere. Our planet Earth is at the center. The Earth has an equator, and the celestial sphere has an equator. This celestial equator is directly above the Earth's equator. So in the sky, there's an imaginary line. It's really not there, but it's more like a direction in space. It's a direction in space directly above the Earth's equator. But if we could draw it on the sky, it would appear up there directly above the Earth's equator. Earth has a north pole and a south pole. And so in the sky, we have a north celestial pole and a south celestial pole. Again, not real spots in space, but more like directions. And we happen to have a star in the northern hemisphere that is directly above the Earth's north pole, or almost directly above it, so almost right directly above. I'll draw a little star there. This happens to be the star Polaris, sometimes called the North Star, because it is directly above the Earth's North Pole, almost directly above the Earth's North Pole. So it's always in the same place all night long. It's always in the north, directly above the Earth's North Pole, near the North Celestial Pole. Again, all of these are not real, happen to be directions in space, but they make it for a convenient discussion. We also happen to have another important line in the sky, imaginary line or direction in space. Besides the celestial sphere and the equator and the poles, we happen to have this other line that's referred to as the ecliptic. The ecliptic is where the sun seems to appear in front of the constellations. It's really caused by our revolution around the sun, as the other video in this week's homework shows you. But for convenience sake, it looks like the sun moves on the celestial sphere. Sometimes notice that the sun is above the Earth's equator. Sometimes it's above the equator, and sometimes it's below the equator. And this is what our seasons are from. When the sun's above the equator for us, it's summer. When it's below the equator, it's winter for us. When it's on the equator, those terms are called equinoxes. The first day of summer, or the first day of fall rather, and the first day of spring are the equinoxes. So notice as this drawing shows that there is roughly a 23.5 degree tilt between the equator and the ecliptic. They are not the same place. The celestial equator, remember, the celestial equator, the celestial sphere, these are all convenient locations. Now, in this week's Starry Night, we're asking you to take a look at some celestial coordinates. So there's celestial coordinates in the sky that are just like longitude and latitude on Earth. They make it convenient for us to talk about where things are in the sky, the same way that an address makes it convenient to tell someone where you live, or longitude and latitude is a convenient place to locate cities on the Earth. So in the sky, we have longitude and latitude. Notice that the longitude lines are not measured in degrees. Rather, they are measured in hours, hours and minutes, and seconds, just like time. 24 hours has the equivalency of 360 degrees. So 1 hour of celestial longitude is equal to about 15 degrees as part of a circle or as part of an angle. So each one of these lines on this chart, particular graph, are shown as 2 hours apart. But they are imaginary lines as well that run in between them of hour marks as well. So 6 hours would be between 6 and 8 hours of right ascension. The longitude in the sky is called right, like the direction, right hand, and ascension. Right ascension is the term for longitude. The latitude lines on this graph are shown in degrees, just like we measure latitude on the Earth. So this one's 30, this one's 60, and then obviously the celestial equator is at 0 degrees. So anything north of the equator is measured in plus degrees. Anything below or south of the equator is measured in negative degrees. And the latitude is referred to as declination, the declination of an object. Declination. So sometimes you'll see these things abbreviated as RA for longitude and DEC for declination, right ascension and declination. The planetarium happens to be a celestial sphere. The projection dome is that sphere, represents the sphere, and so we end up with half a sphere or a hemisphere. So we happen to have the North Pole and South Pole. The horizon is really what gets in our way here. The Earth gets in our way, and we cannot see through the Earth beneath our feet. And so we only see half of the sky at any one time because of the horizon that's here. And we also happen to have another point here, and that is a point that is directly above the Earth's observer, and that is called the observer's zenith. That is the point straight up in the sky. The zenith, it's straight up. So in our planetarium, we'll have an opportunity to re-represent this as a hemisphere. At the very center of the planetarium is a projector that shows all of these objects. And so we also happen to have this meridian. The meridian divides the rising stars from the setting stars. And that represents the highest spot in the sky. So the meridian divides rising stars from setting stars. So we only really see half of the celestial sphere at any one time. If we can chop open the celestial sphere, we get a sky chart that looks like this. And it's really centered on the equator. And notice at the very top, it says that we have an equatorial sky chart. So the equator happens to be this line at 0 degrees that is running directly all the way across this particular chart. So 0 degrees is the latitude. That's the equator. 0 degrees declination. And also, we happen to see the ecliptic. Notice the ecliptic kind of snakes high and low around the equator because the Earth is tilted 23.5 degrees. So we now see also the measurements of declination and the measurements of right ascension. Notice that right ascension is measured to the left. If we look at the top, you can see 0 degrees, or 0 hours, 1 hour, 2 hours, 8 hours, 13 hours, 20 hours, 24 hours, and then, of course, the chart starts over again, back over at 0. And these numbers are reproduced across the bottom. So each celestial object happens to have a location in space that is called its coordinates. And so, for example, this star that I'm circling has some celestial coordinates, and notice it's between 5 hours and 6 hours, and it is between 40 degrees north and 50 degrees north. Sometimes we use the letter N after the degree mark, and we write it just like temperature, 50 degrees, 50 degrees, if that were the measurement. So it's somewhere between 40 and 50. In one of the assignments I'm going to ask you to do here, we're going to get very precise with this and make these measurements. So this happens to have a plus or a north declination, and stars down here happen to be south declination. These stars are in the negative 40 degree range, or we could write it 40 degrees south. So every star on here happens to have a location that's its right ascension, its longitude, and its declination, its latitude. Notice that the equator has a 0 degree of declination. The ecliptic, however, varies between negative 23 degrees declination and 23.5 degrees declination. In the polar region of the map of the sky, we also happen to have a similar arrangement. Notice that we cut this off at 60. The polar chart would go all the way to 90, and it will show the stars near the North Celestial Pole. So we can see here, for example, the Big Dipper is near the polar region, a famous constellation called Cassiopeia, and Polaris is right there, almost but not exactly at 90 degrees north or plus 90 degrees declination. Some other stars here are Deneb, and there's a star here called Capella, and that actually we circled that on the other chart. So to continue on with your starry night, we want you to measure the longitude and the latitude of some stars, and then we want you to find some stars and give us some longitude and latitude. Longitude is right ascension, measured in hours and minutes. A minute is a fraction of an hour, 60 minutes in an hour, and measure degrees, and you can write decimal degrees too, like a half degree, if you want to be that precise. So good luck on that, and if you have questions, please contact me.